Before I start today's lecture, do you have any questions? No? So I continue the discussion on the Monte Carlo simulation of 2D zinc model with Metropolis algorithm. Let me go to the full screen. Okay. So this is the main part of the simulation code. Okay. Yeah. So the major feature is to go over each side. Okay, with the index k, and that was obtained by the x coordinate and y coordinate. Okay, yeah, and then at the side k, and this is the spin. Okay, at the side k, spin is the spin array of the all sides. Okay, so k is from 0 to nx times ny minus 1. Okay? So as I mentioned last time, the new spin is always opposite to the old spin. Okay, so this new spin is the child spin. Okay, so this child, okay, is whether it becomes the new spin at that side, we still don't know yet. Okay, so there's the main, yeah, so this is the main characteristic of the simulation, and this is the stochastic process. Okay, and there's no well-defined okay result until the simulation is done. Okay, and that the outcome depends on the random number. Okay, yeah, actually. So the labeling size is the K1, K2, K3, and K4. Okay, so this is the forward. Okay, so that's the on its right. Okay, forward one step in the x direction. Okay, so it's the side on the right of the k. Okay, and then k2 is the side on top of the k. Okay, so the y is the increased y coordinate increased by 1. Okay, and k3 is the x coordinate is minus 1. Okay, yeah, so so that's the left. Okay, yeah, and this has already taken into account of the periodic boundary condition. Okay, so that means, yeah, when it goes at the boundary, okay, then it wrap around, okay, to the other end, okay, as the its neighboring state, neighboring side, okay, as I explained last time. And then K4 is the bottom, okay, so that means the y is the decreased by 1, and then with the periodic boundary condition. So the I want to compute the energy, okay, of this configuration. Okay, so since only the spin, okay, at the side k is updated, so I only need to compute what has been changed. Okay, so since the spin, okay, k is only interacting with its neighbors, so the change of energy can be expressed in terms of the new spin minus old spin times the sum of all neighboring spins. And if there's a magnetic field, then still have a positive term due to the magnetic field, external magnetic field. Okay, and B field is assumed to be constant for all spins. Okay, so this is the DE. Okay, yeah. So minus of the new spin times this, okay, is the new energy, and then O spin minus O spin times this term is the O energy. So the change of energy, okay, can be written as a difference of the new spin minus O spin. Okay, okay, and then times this term. Okay, so if d is less than 0, less or equal to 0, that means the energy is the new spin will give the lower energy. Okay, in that case, then the new spin must be accepted. So then once this is true, okay, then there's no need to go to this part, okay, yeah. So if you put this and this in the different order, okay, then your computation will be more because every time, okay, you will first go to evaluate this, and this evaluation is a more time consuming, okay, yeah. So since when DE, okay, is less or equal to 0, it must be accepted. The new spin, okay, must be accepted. So the first thing is to test this, okay, yeah. If it's true, then it's accepted. And this or, okay, this does not necessary to evaluate at all, okay, then save time, okay. So if DE is less or equal to 0, then the new spin is accepted, okay. Otherwise, generate a random number, okay, by this random number generator, okay. And see if this random number, okay, between 0 and 1 is less than this, okay. If it's less than the exponential of the minus of delta E over T, okay, then it's accepted. Otherwise, it's rejected. The new spin is not accepted, okay. So if it's, yes, if this or this is true, okay, then accept the new spin. And then the spin at the side K, okay, is replaced by the new spin, except the new spin. Otherwise, the spin at the side K is still the same as the old spin, okay? And that still counts as the new configuration in the simulation sequence, okay? Yeah. So is this algorithm clear? This is Metropolis algorithm. And since this is the loop, okay, so go through each side, okay, so yeah, each side, okay, it try to flip the spin, okay, you flip the spin, is if you are less energy, then it is accepted, the new spin. Otherwise, okay, generate random number, see if it satisfies this random number is less than this. If yes, then it's accepted. So that means the probability acceptance is the maximum, the minimum of 1 and this expression, okay, and that is exactly the acceptance probability of the Metropolis algorithm. Okay, so now I go to the code. Okay. Let me go to a code. So yeah, the same directory is in the cuda-lecture 2025. Okay, so there are many codes here. Okay, yeah. First, I look at this using 2D CPU.cu. Okay, yeah. The reason this code is compiled by the NVCC is because I use the timer. Okay, but the CPU, the GCC, okay, GNUC has its own timer, okay. So actually, in that case, there's no need to use the submit to the yeah, and to run this under with the CPU at the node, okay, yeah. Yeah, the code, okay, has a lot of explanation of the, say, all the observables, okay, all the variables are well defined, okay, by the comment, okay. So the nx, ny is the number of size in x and y direction, and then the total number of size is the nx times ny, and the new spin or old spin at the site in question, okay, at k, okay, and since is the sum of all neighboring spins, and then this is the spin variables, okay, this array, okay. and then the forward and backward index. And then number of swaps for familiarization. As I said, okay, the Monte Carlo simulation initially, okay, the system is still far from the formalized, okay? That means the probability of getting the configuration is proportional to the exponential minus E over KT, okay? So we have to do the simulation, okay, many swaps, okay? Then after many swaps, then the probability of getting a configuration is equal to the Boltzmann distribution, okay? Boltzmann probability, okay? So that is the called formalized, okay? Yeah. And the NM is the number of measurements. And then we do not need to do the measurement for all swaps, okay? So after you simulate for some numbers swaps, then I perform measurement, okay? So this is the intervals between successive measurements, okay? So go through, update each site, go through each site and then do this updating, okay? And this called one swap, okay? But then in order to get the really independent or the correlation is not too strong between the configurations, then we have tried to skip some swaps between the successive measurements. So this is the interval between the successive measurements. So still that number should be very large. So this ND just the display, okay? Yeah, if I want to see how's the simulation going on the screen, then this is the how many swaps between displaying results on the console, okay? Yeah, and then this is the NB is the number of swaps before saving the spin configurations. So after saving the spin configurations, then you can see, okay, exactly how the spin, okay, configuration look like, okay, whether they all aligned to one direction or whether they all random, okay, aligned, that means all spin up or all spin down, okay, yeah, so, and then this is the total swaps at each temperature. So this is total number of swaps, okay, yeah. Suppose you want to go through many different temperatures, yeah, so there's the harmony swaps at each temperature. Yeah, so this is the index, okay, and so on. And then the initial configuration can be cold start. Cold start means all spins are at the same direction. Hot start means the spin is random, okay? Yeah, just generate random number and then see if it's bigger than 0.5 is +1, less than 0.5 -1. Okay, so yeah, T is temperature, B is external magnetic field. So energy is the total energy of the system and total magnetization of the system. So so I think all the variables are well defined. Okay, yeah, so you can just look at it and then you can see, yeah. So so initially, is to try to initialize the random generator, okay, with this machinery twister 19937, okay. So the length of this, I mean the period of this random generator presumably is the 2 to the power 19937. So it's very, very long, okay. Yeah, the seed, okay, yeah, this is a reseed, okay. Even though if we do not enter the seed, okay, then the system automatically, okay, default, okay, there's a default seed, okay. Yeah, but in order to get a well-defined simulation with the same initial seed, okay, so it is a good practice to enter the seed yourself so that you can repeat the simulation, okay, yeah, to check the simulation, okay. So the seed, okay, and then initialize the seed, okay, by your initial seed input, okay, and then the echo, the RNG, okay, when the random generator has been initialized. and then enter the, say, harmonic size in each direction, in each dimension, okay? So, so the forward index, forward, and then the backward, okay, is the, you can see, okay, forward is the I plus 1 more nx, okay? So that means if it's nx, because the I is from 0 to nx minus 1, okay, if it's nx, then it goes to 0, okay? So yeah, similarly for the backward, okay, yeah. So if minus 1 plus nx, okay, then if it's yeah, if I is 0, then it goes to nx minus 1, okay, yeah. So, and then the spin array, okay, and here, this is the swaps for the formalization and the swaps for the measurement, okay, yeah, and so on. Display, and then the interval for saving the spin configurations, and then enter the temperature, okay. So, enter the external magnetic field, okay, yeah, and then whether initial spin is as a cold start or hot start, okay. Presumably, no matter you use the hot start or cold start, okay, at the end, I mean, after enough number of swaps formalization, then they should be all reaching the thermal equilibrium, okay, with the probability getting a configuration proportional to the Boltzmann distribution. Yeah. So this is the cold start, okay, set all spin to be 1, it's a cold start. For a hot start, as I said, okay, to get a random number, see if it's bigger than 0.5, bigger than 0.5 is set to +1, otherwise set to -1. Okay. So this is the hot start. So this is a random, okay, yeah. So we have an output file to have the data or the result, okay, and also this is the spin configurations, okay, saved in the file, okay. You can always check, okay. Yeah, first, I pin out the exact solution, okay. So for 2D sync model with 0 magnetic field, we have an exact solution that was obtained by Onsaka in 1944. Okay? So as I said, okay, yeah, here, this is the routine, okay, exact 2D, and this is the derivative functions, okay, used to compute the exact solution, okay, yeah. Yeah, only for the 2-dimensional sync model, there's a exact solution for the 0 magnetic external magnetic field. So for 3-dimensional sync model, so far there's no one has obtained the exact solution. Okay, it's a very challenging problem, and yeah, the common consensus is the 3-dimensional sync model does not have an exact solution. Okay, but this is only a consensus belief. Okay, dogma. Okay, yeah, unless one can prove, okay, the exact solution does not exist. Okay, then yeah, then we know for sure. Okay, otherwise, yeah, everyone still has a hope. Okay, to try to obtain the exact solution. Okay, yeah, it happened. Okay, yeah, some people claim, okay, they obtained the exact solution, but later, okay, people find out there's some error in his derivation. So yeah, so it's not easy. Okay, so it's a very difficult mathematical problem. So for b equals 0, then I can obtain the exact solution using the exact solution to compute the values, okay, of the energy and magnetization. Okay. So this magnetization is the spontaneous magnetization. Okay. So the 2-dimensional sync model is a very interesting system because it has the spontaneous stimulus breaking. Okay. So at high temperature, okay, the magnetization is 0. Okay, because all the spins are random. But then at low temperature, around T over K less around 2.2 something. Okay, depends on the size of the lattice. Okay, the exact solution is for the infinite size of the lattice, infinite lattice. Okay, then it has a phase transition. Okay, so all the then the magnetization, okay, becomes 1 plus 1 or minus 1. All spins are aligned. Okay, so this is the spontaneous, because this is there's a symmetry of the Hamiltonian. Okay, the symmetry Hamiltonian is that all spin up or all spin down has the equal energy. Okay, so these two are ground state. Okay, but then spontaneous magnetization is that once your system is sitting in one of the ground state, then it cannot go to the another ground state, because it takes infinite amount of energy to reach one ground state, from one ground state to another ground state. Okay, so this is called spontaneous breaking. The vacuum breaks the T2 symmetry. Okay, but the Hamiltonian has such a T2 symmetry. Okay, and this spontaneous breaking has a far-reaching implications in modern physics, in modern particle physics. Okay, yeah, and the standard model and all this actually based on this spontaneous series breaking. Okay. Okay. Yeah. You see, if B equals 0, if there's no external magnetic field, then I have an exact solution. Otherwise, I don't have an exact solution. Okay, in that case. But for the simulation, I always have some simulation result. Okay, but this is only a finite lattice. Okay. Yeah. So this is the simulation output. Okay. Yeah. And the timer. Okay. Okay. So this part is the simulation algorithm, Metropolis algorithm simulation as well. So this is the go through all total number of swaps. Okay. Yeah. So if the swap is bigger than the NT, okay, yeah, bigger than femorization, and then after femorized, then every so many swaps between successive measurements, then I will do the measurement. Okay. So measurement is the total magnetization, sum of all spins of the all sides. Okay. And then compute the energy. Okay. Of the entire system. Okay. So this is the total bond energy. Okay. Yeah. Yeah, you can see, okay, this is only, I only have to sum over the spin K times the spin K1. Okay, K1 is the X plus 1. Okay, and this K2 is in the Y plus 1 direction. Okay, so then in this manner, okay, yeah, all bonds energy are summed. Okay, yeah, you don't have to sum 4 directions, because then it will be overcounted, or you have to take a factor 2 out of it. Okay, and then the total energy is the energy between the spins, and also the energy between the spin and the external magnetic field. Okay, so I accumulate. So after I swap over all sides, okay, and add all these spins and all these energies and then magnetization. So I get this, okay, accumulator to TE, and then the count, how many counts goes to count. So at the end, okay, I do the normalization, okay, save the raw data, okay. So this is only each swap, okay, the energy, how much energy, and then the magnetization, okay. So save the raw data, yeah. And if the satisfy this criteria, okay, because every ND swaps, then I would like to display the result. Okay, so this is the result. Okay, so this is the per site. Okay, so normalized by the number of sites, and then normalize the count, okay, how many measurements already been done, okay? So this is accumulated average, okay? Yeah. So if if every NB, okay, is the after how many swaps, okay, then I should back up the spin configuration to the file, okay? So I'll put the spin configurations, okay? Yeah, and then yeah. So so this is the end of the simulation, okay? And then here I just pin out the exact solution again, okay? Because in the beginning, okay, and at the end, so that it is for the convenience of comparison, okay? And stop the timer and count how many gigaflops and how much time has been used, okay? So finally display the destroy the timer and also feed the pointer of the GPU, okay, of the random number generator, okay, yeah. Okay. So the exact solution, okay, yeah, so even there's exact solution, but it's in terms of the elliptic function, okay, so it's still very formal, okay. So in order to get a number, then you still have to do the numerical evaluation of these special functions, these elliptic functions, okay. So, so there's several routines for evaluating the elliptic integrals. Okay. Okay. So the code, and then all the codes are made by there's a make file. Okay. Yeah. So just type the make file, and then all different codes are compiled. Okay. Yeah. So for the using CPU, CU. Okay. Yeah. If you have to use the timer, okay, then you must have to submit the job to the condo and then run it at one of the GPU nodes, with the GPU card, such that, okay, the timer in MVCC, okay, in CUDA can be used for doing the timing. Yeah. Alternatively, you can also using the timing function in GCC, okay, and you can look going back to the vector addition, okay, then there's a direction for the CPU, and then you can see there's a timer, how to implement the timer with only the CPU code, okay. In that case, okay, if you run the CPU code at the console, okay, then you are using the CPU in the head node, okay, rather than in the GPU node, okay, and the CPU are not completely the same, okay, so you will see the different performance, okay. So there's a CMD file, okay. So for the CMD file, this so CPU, okay. So for CPU, okay, you have to select the M type. M type is a CPU, okay, and then you would see whether the CPU node is the CPU of the any GPU node is available. Okay, yeah. So this is the initial directory, is the working directory, and then here I just select the one submit the CPU, and then the input CPU and the output CPU. Okay. So for the input CPU is this. Okay. So this okay. So this is the SIP. Okay, this is SIP, and then the number size in this dimension is 128. So this lattice is 128 by 128. Okay, and then I use 1,000 swaps for the formalization. Okay, yeah. I don't know whether this is the sufficient. Okay, but I just try it. Okay, if I see, okay, the measurement, okay, yeah, really depends on the initially, okay, it changes a lot, okay, then I know is not thermalized. Okay, so the initially the configuration is the system is not reaching the thermal equilibrium or getting a configuration. The probability of getting the configuration is not equal to the Boltzmann factor. Then in that case, okay, such a configuration should be discarded in order to should not be used for doing the measurement of the OI. Okay. And then the number measurement is again 1,000. Okay. And then the interval between successive measurements is 10 swaps. And then display interval, that means every 100 swaps, I just display the accumulative average of the E and energy and the metallization. Okay. To see whether how the simulation goes. Yeah. And then this is the saving the spin configurations. Okay, yeah. The reason of saving a configuration is with the spin configuration, you can always do any measurements. Okay, using that configuration. Okay, so this is the actually this is the major result of this. Yeah. Okay. Of course, you can also saving the energy or metallization. Okay, yeah, for this route. Okay, so this is the one way, or either you save the spin configuration, then from the spin configuration you can do the measurement of the energy and the metallization for this configuration. Okay, or you can just measure energy and metallization and then save that as for this configuration. Okay. So, okay, so this is the temperature. Okay, so I set temperature is 2.4. Okay, so 2.4 is higher than the transition temperature. Okay, so it is in the disordered phase. That means the metallization is 0. Okay, yeah, you will see. Okay, and the external magnetic field. Okay, and then the initial spin configuration is 1. That means they start with a random spin configurations. Okay, so this is the input file. Then what's the output? Output of the CPU. Okay, so let me move it. Okay, so you can see. Okay, yeah, yeah. After 1,000 measurement. Okay, so because I do the thermalization. Okay, so you can see. Okay, yeah, 1,000 is rough for thermalization. Okay, so so I do one measurement every 1,000, every 10 swab. Okay, and I want to do 1,000 measurements. So the total number of swabs, okay, is 11,000. Okay, so you see. Okay, okay. So each one is 100. Okay, separated by 100 swabs. Okay, so 11, not 11,000. Okay, is 10,900. Okay, yeah. So you can see. Okay, the energy per site. Okay, is quite close to the exact solution. Of course, it cannot be exactly the same. Okay, because this is for the infinite lattice. So this one is only 128 by 128. So it's a finite lattice. Okay, and also the metallization here. Metallization here, presumably for infinite lattice is 0. Okay, exact 0. Okay, but here is just a small number, and it's fluctuating. Okay, it's fluctuating. So if the lattice is getting back bigger, okay, this number will be smaller. Okay, Yeah, you see, because the fluctuation, one spin, okay, out of 128 times 128 spins, it will be a small number. But in this case, there must be some more than just one spin fluctuation, okay? Yeah. So that means that even in spin up and spin down, there's an imbalance. And then you will see such a net magnetization, okay? Yeah. But if the system getting larger, okay, and then this deficit, okay, becomes small compared to the total number of site, okay, and then the deficit of the magnetization per site will be getting smaller. Okay. Yeah. So the time used is about 5.5 second. Okay, and the gigaflops, okay, is 0.2 gigaflops. Okay, so this is the CPU running at the CPU node. So in that case, I have to look at the condo log, okay, in order to know which GPU node has been used. Okay, is the TIVA QCD218. Okay, the CPU of this node did this computation. Okay, yeah, so yeah. So there's the simulation. Okay, yeah. As I said, okay, I can run this code at the console. Okay, at the head node. Okay, in that case, the NVIDIA CUDA timer, okay, does not work because there's no GPU cards in the or at in the head node. Okay, so but anyway, let me show you. Okay, how CPU. Okay. Okay. So you can see, okay, the simulation, yeah, just looks like this. Okay. And this is the accumulative average. Okay. So you can see, okay, processing time for CPU is 0 here. Yeah. Because the CUDA timer does not work, okay, for the handle. Okay. But the results are the same, okay, actually. Okay, the result, okay, here is exactly the same as what you saw in the output file. Okay. Okay. Yeah. So you have to submit the job to the condo in order to the node, GPU node. Okay, has the GPU. Then the CUDA timer will work. Okay. Okay. Any questions? Any question about this simulation of 2D sync model with Metropolis algorithm? So with the simulation, with the spin configuration, okay, yeah. Let me back to the slide, okay. 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 Full screen. Let me put on the power. Okay. Yeah. Let me see. We don't see anything. Huh? Okay, here. Okay. Yeah. Full screen. Okay. I don't see it. Huh? Okay. Yeah. Okay. So in order to measure any observable of the spin of a spin configuration, okay, So after filmarized, probably you're getting the spin configuration sigma. Okay, so that the spin configuration is all the spin, okay, of this lattice. Okay, yeah, is proportional to this. Okay, then the expectation value of any observable. Okay, initially we have to sum over all configurations, right? But for a simulation, okay, I can only sum over the configuration generated with this probability. Okay, then so this is the sigma take in the sequence of the simulation. Okay, so depends on what's the m. Okay, then the result. Okay, will be different and also have the error. Okay, proportional to 1 over square m. So that means the more measurement. Okay, after formalization, the more measurement you do, then you get a more precise mean value and also smaller error. Okay. Yeah. So this is the feasible way of evaluating such a summation. Okay, of so much terms. Okay, which you cannot obtain by direct summation over all different configurations. Okay. So Monte Carlo simulation to get a approximate solution, okay, is the only way we can get the reliable result from this. Okay. Yeah. Similarly, for the magnetization, okay, is the observable, okay, is this sum over all the spin of the entire system, okay, and then divide by number of size, okay, that means the average magnetization, that's the magnetization density, okay. So it becomes this, okay, yeah. So it's easy, okay, sum over all this. And the energy density is this, E sigma, okay. And then in this case, yeah, you just measure the energy of this configuration, okay. And then some one also, so this energy density of uh, this configuration, okay, and the average over M configurations, okay. And then the error estimate is the error, it should be proportional to 1 over square M. Okay. Okay. So this is the how what was the sample code have been implemented. Okay. Yeah, measure the magnetization density and also the energy density. Okay. Any questions? Yeah. So this is the simulation using the using a CPU. Okay. So now the question is, how can we do this simulation with GPU? Hmm? Can we partition the lattice and then have each block, okay, doing the simulation? Okay, is it possible? But then you see, there's a issue is that, okay, there's a two block. Okay, one when the simulation goes to the uh, boundary of this block, okay, then this may be in this block. If this block is at the uh, yeah boundary of the grid, okay, of handled of this block handled by this GPU, then no, this is block, and yeah, then the boundary is in the next block, okay. So it's possible that these two threads, okay, maybe updating the site, okay. So of the neighboring block, okay, yeah. So another thread is updating the, okay. Then uh, you are getting the uh, unpredictable result, okay. Oh, okay. So it's better to say have a scheme, okay, such that this will not different threads, okay, of different block, okay, will get the incorrect simulation result by just because when that spin is updated and then the other is label, okay, does not get the latest spin value, okay, out of it, okay, and then you end up with a incorrect result, okay. So unlike the CPU, okay, only just successfully go over each side successfully, okay. So so we must have to come up with a way, okay, to using how can we simulate the using auto with as a parallel computation, okay. Okay, so so let me go to the the next lecture slide, okay, So so how to perform a parallel computation of Monte Carlo simulation 2D sim model, okay, so let me see, you get this. Look at this. Okay, you see this. Okay, good. Let me, okay, here. And then this is the parallel updating with the even not scheme, okay. So this is the common scheme such that I can use more than one thread, okay, doing the parallel computation, doing parallel updating, okay, without messing with other updates, okay, And then how can I implement this parallel updating with the even not preconditioning, even not scheme, okay, So this you already know, so I don't have to repeat, So even not scheme, okay, or this checkerboard scheme, okay. So the main idea is group the lattice into two sets, even size and odd size, okay. So labeling size of any even size or odd size, and vice versa. Then all the even size and odd size can be updated in parallel. That means I first update the even size because all the odd size are fixed, okay. The spin are fixed. So I update the even size, then since all these labels are fixed, okay, so we can update it without any controversy, okay, So so the updating can be first performed on all even size in parallel, and then go to update all odd size in parallel. So then this completes one swap, okay. So that means I do a parallel, okay, but the parallel computation only on the even size, okay, or only on the odd size, okay, In that case, there's no two the labeling size of each updating site, okay, will not have any other size since other sites are odd size, okay, and then they are fixed, okay. Similarly, if you are updating the odd size, then the even size are fixed, okay. So the updating can proceed without any ambiguity. Of course, this even not scheme can only work for models with the nearest label coupling, okay. If it is the interaction between the spins, okay, is not just nearest labeling, can be very far away or infinite range, then this scheme does not work. Okay, you have to come up with another scheme, to make this parallel for the parallel computation. Okay, so next at this moment, just for the Ising model with the nearest label coupling. Okay. So now consider there's a 4x4 lattice. Okay, so this is the 16 sides. Okay, 4x4, 16 sides from 0 to 15. Okay, and with the periodic boundary condition, so this side here, the label, okay, the the right hand side is this side. Okay, so similarly for this side, the labeling is the in the y direction. Okay, is the 2. Okay, yeah. So this is the even side, and this is the odd side. Okay, so you can see. Okay, when I update the odd sides, the even side are fixed. Okay, so I update the side. Okay, I only need to know the what is this label are all even, and they are fixed. Okay, and similarly for the even side, okay, the odd side spin are all fixed. Okay, so I can do the updating. So okay, so the threads only these threads are only acting on this even side. Okay, so has no interference. Okay, so updating here has nothing to do with the updating here. Okay, yeah, because I don't need the spin at this side in order to update this side, the spin of this side. Okay, so because it's the only this label, so only this 4 spins is relevant to the updating of this spin. Okay, and these 4 spins are fixed. Okay, because they are odd. Okay, so I'm only updating the even side. Okay, spin. Okay, so in order to label the even side and odd side, then you have to map the okay. So the even side is okay. Is this 0, 2, 5, 7? Okay, 0, 2, 5, 7, 8, 10, 13, 15. Okay. So that means more or less you are collapsing the rows. Okay, and then you obtain this. Okay, yeah. So yeah, okay. You see, yeah. So you just skip all the green. Okay, and then you get the red. Okay. So you can see. Okay, in this case, okay, you are reducing the rows. Okay, in by 2. Okay, yeah. So for this even size, okay, you still have to think about this is for the index this is the deal. This is 1, 2, 3, 4, 5, 6, 7. Okay, but this index is different from this index original in the original site lattice. Okay, the full space. So from even space to full space. Okay, so that means yeah, if I know there was this 0, 1, 2, 3, 4, 5, 6, 7. This the even the site. Okay, IE. Okay, on the even lattice. Okay, even space. Okay, so I want to convert to its coordinate in the full space. Okay, to this. Okay, okay. Then what we do is doing this. Okay, if you have the index in the even space, then you 2 times this and then mode the nx, you get the x position. But this is not the final one. Okay, and then for the y is 2 times 2 divided by nx and then mode nx. Okay, so this is 1. And then you have the parity. Okay, x plus y mode 2, you get the parity. Okay, and then x as the parity becomes the real x. And then once you get the x, then you get the using the y, and then together you get the I. So this index is the index in the full space. Okay, that ranges from 0 to 15. Okay, okay. For the IE, okay, only range from 0 to 7. Okay, yeah. So this is the prescription. Okay, and it doesn't take too long for you to understand why this is reasonable in verbs. Okay, so yeah, similarly for the odd size. Okay, so you can see. Okay, your odd size becomes the arranged in this way. Okay, so becomes this. Again, okay, the space becomes yeah 2 times 4. Okay, yeah, so that means the y is the only 2. Okay, x is still dimension is 4. Okay, so if you know the IO is from 0 to 7, then you can obtain this position. Okay, in the full space. Okay, x and y. But then the parity, you have to adjust for the parity, okay? And then the parity is set, add to the x, okay? And after that, with this x and then the y, then you can reconstruct the position, okay, in the full space. Okay? So, yeah. So with this prescription, then, yeah, this is the implementation, okay? Yeah, so IE from 0 to half of the size, okay, half the size, okay. So if the n is 4, then the total number size is 16, okay, and then half size is the 8, okay. So this is going from 0 to 7, okay. So with this IE, then you obtain computer X, Y, and then this is exactly the description I have in this uh, here, okay? And then for the odd space, okay, to full space, okay, yeah, okay? And then, yeah, so this is the answer, okay? So using this code, okay, when you run it, okay, then you can see IE from 0 to 7, then you get the X and Y, okay, and you exactly get the correct answer, okay? 0, 2, 5, 7, 8, 10, 13, 15. Okay. Similarly, for the odd index, okay, the index in the odd, okay, space, okay, then go to a full space, you get this. Okay. So the code is here. Okay. Yeah, you can look at the code and then you can test it. Okay, and exactly reproduce this. Okay. And this is the general. Okay, for any lattice, okay, for any, say, this two-dimensional lattice, okay. Yeah, if you have go to 3-dimension, and then you have to just change the formula, okay. Okay. So that means the parallel computation or even odd scheme is the first update the even spin, okay, update the spins on the even side, okay, yeah. So IE, okay, from 0 to 1/2 of the lattice size, okay, and then I get this position X and Y. Once I get the X and Y, and then this. So this part is the using the even not preconditioning. Okay, yeah. So so the I is the side in the full lattice. Okay, then the rest is the same. Okay, okay. So this is the update even side, and then update the odd size. Okay, okay. So complete code is this: using to the CPU even odd dot C. Okay, yeah. So let me go to a code. Okay. Okay. Using CPU even odd dot C. Okay. So I just point out the difference. Okay. So first, update the even size, okay? And then update the odd size, okay? Yeah. Okay. Oh. Then the rest is the same, okay? Yeah, measurement, doing the measurement, all this the same. Okay, so even odd, okay. Yeah, just using the different command files to run the different options. So okay, okay. So again, using the same input file, okay. Okay. Yeah. Oh, someone is using. This is working on the homework 6. Okay. Yeah. Let's see. Example, he would just submit to another node. Okay. Yeah. While the other job is running. Okay. Yeah. Take some time to initiate. You know how come the condo seems. Okay. Done. 116. Yeah. Let me see. Tail. Now CPU start. I just compare this. The one. Yeah. Output CPU. Okay. And then this is output even odd. Okay. You can see. Okay. The results are different. Okay. Because they are different simulations. Okay. Okay. Yeah, but the results are compatible. Okay. Yeah. 1.2038. Okay. Yeah. And then the time here, even not okay. It takes more time. Okay, you see? Yeah. Yeah, for even not, yeah, because for the CPU, okay, for the CPU, and yeah, it only has one phase, okay. It's better just go for it. You see there's a conversion, okay, yeah, between the sites, okay. So the mapping, okay. So it's not the most uh, efficient code. Okay, yeah. Of course, I can make it more efficient. Okay, but this is just yeah. So for the CPU code, okay, yeah. You see the reason why it takes more time is because it spends a lot of time to doing the convert to the from the even index to the full index. Okay, here this part. Okay, yeah. Every swap. Okay, yeah. It has to do such a conversion in order to get this. Okay, yeah. This mapping actually can be done just once. Okay, yeah. So you have to change the code to make this mapping. Okay, because it's always the mapping is always the same. Okay, yeah. There's the table I just showed you. Okay, that mapping is always the same. Okay, for each swap. Okay, so now is doing extra computation here. Okay. And similarly for the updated size, okay, computing this X and Y, okay, compute the I, okay, from the IO goes to the I, okay, yeah, takes time, okay, so this reason it takes longer, okay. So for the CPU, okay, there's no point you're using the Ethernet preconditioning, okay. But for the GPU, okay, I really have the many threads, okay, and many blocks, okay. In that case, okay, the Ethernet preconditioning is necessary. Otherwise, I cannot do this. I do the parallel computation. Okay. Okay. Let me back to the slide. Okay. 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 So full screen. Okay. So now GPU implementation. Okay, using the global memory. Okay. Actually, there are many different ways, okay, of doing the simulation with the GPU. Okay, so yeah, I just telling you this is one possibility. Okay, yeah, suppose I have a ladder size 16 by 16. Okay, so I just have a block dimension 2 and 4, and then the grid dimension is of 4, 4. Okay, yeah, the block dimension is 2, 4 is because anytime I only use the even lattice or odd lattice, okay? So that means in the block size in the X in this, okay, is a 2, okay, here is a 4, okay? So yeah. Okay. Oh yeah, there's a GPU implementation with global memory is that okay? Yeah, it can perform several swaps at each core. Okay, so yeah, use the CPU or GPU to generate the random number, generate the random number. Okay, so you have options. Okay, yeah. So in the sample code, okay, I always use the CPU to generate the sequence. Okay, and then and then send it to the GPU for use. Okay, yeah, but you can also have the GPU to generate the random number, okay, for designing the spin, is that new spin is accepted or not, that in that step, okay. So also you can put the entire simulation in the GPU, okay. Yeah, in the Metropolis algorithm, okay, when the change of energy is bigger than 0, in that case, you have to compute this factor and then generate a random number, see if the random number is the less than this factor, then exponential minus delta E over KT. So since the spin values are finite number possibilities, okay, yeah, so you see the spin, okay, the delta E is like due to the different spin, new spin, all spin changes times the sum of the spins of this surrounding or these labels, okay? And the number possibility of the sum of the surrounding of these labels, okay, the spin are fixed, okay, because they are finite values, okay. This is the +1 or -1, okay. So that means that all possibility of the delta E can be known beforehand, okay. So I can save this computation by generating a table, and then once I know the say the spin, okay, how what's the sum of the spins of these labels, and then what's the old spin and new spin, okay, of this. So I only need to compute this index, and then I can from using this index to get this number, get this value, okay, exponential value from the table, okay, instead of doing this computation again, okay, yeah. So they will save a lot of time, okay. So so that means generate the table, which includes all possibilities, okay, of the delta E, okay. Then, yeah, this factor can be, you just don't need to compute in the beginning, okay. Yeah, just compute in the beginning and don't have to be compute again. Yeah. Okay. So so let me go to the next one. So first, the mapping of the Fed, okay, to the psi index, okay. So the Fed index is in a block of size Tx, Ty, okay. And then since this is the even side or odd side, okay, so the size of the Tx, okay, is 1/2 of the Ty, okay. So the largest size it handles is this, okay. Suppose this is the block dimension 2, 4, okay. Yeah, and then the size of lattice actually is 2 times the Tx times Ty, okay. So this is the number of phase in the x direction and number of phase in the y direction, okay. So the IE, okay, is the Fed index x plus the Fed index y times the block dimension x, okay. So the nx that means this, okay, this, okay, nx is 2 times the block dimension x, okay, so this is the nx, okay, and this nx, okay, is the capital NX, okay, is the large size x in x direction, okay, in of this block, okay, of this lattice, okay, and the NX is the total number of size, okay, in the entire lattice, okay. So that means so you have the times the grid dimension in x, okay. So go over the even size, okay, i.e. is this. And then with the IE, then you get the x position and y position. And then, yeah, and the x position adjusted by the priority. Okay. Okay. And then add the offset to get its position in the full space. Okay, so you add this index times block dimension index, block index at x direction. Okay. And then the block dimension y times the block index in y direction. Okay. So this is the y. Okay, so this is the offset. Okay, so you know which block. Okay, there is the which block. Okay, then you have to adjust the location of the zero of this block. Okay, of the origin of this block. Okay, and then with this after adding the offset, then just get I of the I is the lattice side of the entire lattice. Okay. And then parallel updating all spins at all sides. Okay. So each thread, okay, is updating the spin at one side. Okay. Yeah. And all even sides have a corresponding thread to handle it. Okay, in this grid. Okay. So that means when you update, then all spins, all even sides are updated. Okay, at the same time. Okay, but they may not finish at the same time because at some site, okay, delta E is less than 0, then it doesn't have to compute the exponential, okay, function. Okay, the Boltzmann factor. But in case delta E is bigger than 0, then it has to compute the exponential function, okay, the Boltzmann factor. Then that will be slower, okay. So not all threads finish the updating at the same time, okay. So yeah. So at the end, okay, you have to syn all the threads, okay. But syn threads only syn all threads in one block, okay. You cannot syn all threads in all blocks in the entire grid, okay. You cannot do that, okay. You have to you cannot just use simply using the syn thread, okay, to do this, okay. Yeah, there's another way of how to syn all threads in the entire grid, okay. I'll tell you later, okay. Yeah. So do the same for the odd side, okay. Yeah. And then after that, then yeah, so this is for the after you update all the spins, okay, even side and odd side, and then you just do the Metropolis, okay, yeah, algorithm, okay, and then yeah, to whether you so this is the for the even side or odd side, okay, yeah. So this is the you can let me go to the version 1, okay, cool, yeah. Yeah. Using the global memory version 1. Here. So this is the kernel, okay? Yeah. So this is the first, go over the even size. Okay. And then do the updating. So to update all the even size, okay, and then the thin threads. Okay. And here I have the note here, okay. Thin thread only applies to all threads in the block, but not all threads in the grid, okay. So not all blocks are synchronized, okay. So if two simulations start with the same randomology, they do not necessarily get exactly the same result. Okay. Yeah. One way to avoid this is to have the update even odd size with the two separate kernels. Then it's in the version 2. Another way is to use the method of the cooperative groups, which is only valid for GPUs with compute capability bigger than SM60. Okay. So for this 1060 is a 6.1, so it's possible. Okay, compile with CUDA 9.1 or higher. Okay, so CUDA bigger than 9.1. Okay, and that's in the version 3. Okay. So this is the remark here. Okay, so I will go to the version 2 and version 3 later. Okay, so at this moment I have the update of the even size first, and then update the odd size. Okay, update the odd size. Okay. So the main code is just here, quite, this is I use the constant memory, okay, because this FLX, okay, and the BBY, okay, is the forward and the backward movement, okay, at each side I, okay. So I copy this to this location, okay, and that's the constant memory because this will not be changed for the for this entire simulation. Okay, so then this will takes less time for the GPU to get this, okay, FW, BW, okay, yeah. So this is the CUDA memory copy to symbol, okay. So this copy to the constant memory, okay, yeah. Yeah, this is the setting the number of threads per block, okay. Yeah. So that's the for the even not updating, okay. Mm. So allocate this spin variables and also the random numbers, okay. So I have these random numbers at each site, okay. I have the random number for it, okay. In case it will be used for decide whether is when the delta E bigger than 0, in that case, I need a random number to decide whether it is accept or not by comparing this random number to the exponential minus delta E over KT. Okay. And then they copy the spin, okay, yeah, from the device spin. Yeah. So initialize this and then also create a timer. Okay. So so copy the random numbers, okay, sequence, okay, to the device, okay, and then Mendix kernel metropolis global memory, okay, yeah. So the kernel you already seen, okay, I already showed you, okay, yeah, and then yeah. So this is the for formalization, okay, and then again, okay, this is the so this is the RNGMT, okay, so generate NS random numbers, okay. So this is the routine is here. Yes, here, okay. Just generate a sequence, an array of the random numbers with uniform distribution between 0 and 1. Okay. Because yeah, at each swap I need at most this number of the one random number, and yeah, if it's needed, okay, at one site, okay, but it will not be more than just one site for this swap, okay, for one swap. Okay. Okay. So this is the after formalization, then it starts the updating, okay. Then in that case, okay, yeah, when it doing the updating, okay, if it is at the swap, it should be doing the measurement, then just copy the spin out to the CPU and then do the measurement at the CPU, okay. Yeah, when it needs to display, then just compute the accumulated average of the energy and magnetization. And then when it's need to back up the spin configuration, then do this, copy the spin configuration from the device, from the GPU to the global map to the system memory in the CPU spin, okay, and then pin out, okay, and finally this, okay, so okay. So now I can, using the same lattice size, okay, yeah, say input GPU, okay. So again, it's 128, okay, by 128 lattice, okay. And all parameters are the same, except now the block size is for even or scheme, okay. It's a 48, okay, yeah. Okay. And then there's the command file for the job GPU version 1. Okay, so you can see it. Okay, so this here. Okay, yeah, here first. Okay, and then I run it the second time. The second time is the say, yeah, with the same seed, but then the second time you may not getting the same result. Okay, as I don't have to repeat the because I can just show you the result. Okay, so tail of these two files. Okay, first, actually I can GPU version 1. Okay, more. Okay, so this is the simulation. Okay, so you can see. Okay, compare this. Okay, you can see this. Yeah, is non-zero compared to exact solution because it's the final lattice. And then the energy density is quite close to the exact solution. Okay, and the time is about 3 seconds. Okay, and then compared to the CPU is about more than about 5.5 seconds. Okay, so gigaflops is 0.2. Okay, so it's a 0.4. Okay, 0.2 something. Okay, so it's the almost 1.7, 1.8 times speed up than the CPU, even for this small lattice, 128 by 128. Okay, so I can show you this tail. Okay, Monster tail box. CPU version 1. Okay, so you can see. Okay, this is about 5.5 second. Gigaflops of 1.2. Okay, for GPU is 3 second, and then the 0.4, 0.41. Okay, so it's I think 1.7, 1.8. Okay, of that. Okay, so yeah. Okay. So this is the version 1. Okay, and if I do the simulation, okay, again, try to repeat the simulation, but then I get a second different results. Okay, yeah. So I have this second. Okay, I'll GPU version 1 second. Okay, second, that means I do it exactly just run it again. Okay, so second time. Okay, and then okay, so let me compare the end result. Okay, then you know the simulation different. Okay, yeah, even though both are consistent with the exact solution. Okay, yeah. Mm. Okay, so this is the first one. First one is this. Okay, and then second one, I got this. You can see these two results are different, right? Why they are different? Because the simulation, okay, you see, yeah, even the sequence is the same, okay. I mean, the random number sequence is the same, okay. But yeah, the thread, okay, because they yeah, they are not synchronized, okay, at the same time, okay. Yeah, so that means, yeah, when one board is synchronized, all threads in one board is synchronized. Okay, but then this synchronization is different from the synchronization of another block. Okay, so this will give you the different when you go to the next the simulation. Okay, then you get a different result. You could have a different result, even though this is all valid simulations. Okay, they are all both valid. The first one and the second one are both valid. Okay, but since the synchronization, not all threads in all blocks are synchronized. Okay, then you will get such a different simulation. Okay, okay. So in order to avoid this, then we have to put the even and odd, okay, updating into two different kernels. Okay, then when I finish all the updating of the even spin, then after that, then all the even spins are all blocks are synchronized. Exit, okay, exit it, and then do the updating on the odd size. Okay, then you put in two different kernel rather than in the same kernel. Then the results, second simulation, will get exactly the same result if they start with the same seed. Okay, random number seed. Okay, and the same condition, initial condition. Say both are start with the same initial random spin configuration. Okay, and then the random number seed. Okay, is the same actually. Yeah. So that is the one I initialize the random number generator is a 1, 2, 3, 4, 5. Okay. So for the second version, okay, second version. Let me go to second version. Okay. So so go to the transparency. So the second version is the separate the updating of the even side and the odd side into two different kernels, and then call the kernels. Okay, first call the even updating and update the even side, and then update the odd side. Okay, so there's the only different thing. Okay, rather than putting this updating of the even and odd, okay, at the same kernel. Okay, in the same kernel. Okay. So in the same kernel, then maybe some of the blocks, okay, you finish, and then you would just from even size, and then you go to updating the odd size. But while other blocks has not completely done yet. Okay, so for the GPU kernel, okay, a basic assumption is that all blocks can be executed independently. Okay, and without any, the order doesn't matter. Okay, so this is the basic assumption. Okay, but in this case, okay, the order really matters. Okay, you have to wait all the even spins are updated before updating the odd spin size. Okay, then the result is repeatable. Okay, otherwise, okay, depends on which sublattice already been updated. Okay, even though these are completely valid simulation. Okay, but still, okay, you get a different result. Okay, the simulations satisfy the still satisfy the detailed balance. Okay, valid simulation. Okay, yeah. Yeah, in order to guarantee, okay, every time you start from the same initial random seed, you get the same result. Then you have to put this two different updating into two different kernel. Okay. Then the simulation can be repeated. Okay. Once you start with the same seed, okay, then the same simulation will be repeated. Okay. That is repeatable. Okay. Yeah. Okay. Let me look at the try to give you the kernel result of kernel 2. Okay. Version 2. Okay. 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 Yeah, I don't go to the code of the version 2 code. Okay. Yeah, it's basically just what I show you in the in the slide. Okay. Let me show you the result. Okay. So now I run the version 2 the first time and the second time. Okay, with the same input file. And then both results are the same. Okay. As you can see, okay, difference of the GPU version 2, and then the output of the GPU version 2 second time. Okay, you see everything else is the same, except the time is slightly different. Okay, yeah, because you cannot expect the time is completely the same. Okay, because that depends on the status of the GPU at that moment. Okay, and then the CPU also, yeah, has some influence. Okay, to this process. Okay, to the total time. Okay, yeah. But it's close enough. Okay, so just 6 millisecond difference or 7 millisecond difference. The most importantly, okay, is this the spin configurations. Okay, are the same. Okay. GPU version 2 tail. Look at the tail. Okay. Yeah. Okay, you can see. Okay, this sequence exactly the same. Okay, this is at the end already. Okay, so yeah. So the spin configuration is exactly the same, okay, for these two simulation. And because both of them, okay, starting from the same random number seed, okay. 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 Now besides the version 2, okay, and there's another way of doing the synchronization for all threads in the grid, okay. Yeah. Um, so this is the called the cooperative group, okay. Again, let me switch back to the lecture slide. Okay. So this is the version 3, okay. Now I only have one kernel, okay. I don't separate into two kernel, okay. Yeah, but then I need to use this cooperative groups, okay. And then the kernel, okay, the code, okay, slightly different, okay, yeah. Is that you have to see, so this is what is the difference is here, okay, in the both lattice. Namespace CG equal to cooperative groups. And CG grid group, okay. Yeah, so this grid, okay, so Fed index of the Fed group. Okay, so this is the Fed index. Okay, so for this, so updates spin all in this, and then the you see the synchronize all Feds in the grid, in the entire grid. Okay, so it's different from the syn Fed. Syn Fed is only synchronize the Fed, all Feds in one block, and has nothing to do with another block. Okay, but this one syn G, okay, says synchronize all Feds in the grid. Okay, so this is the difference. Okay, so yeah, it needs to use this cooperative group in order to do the synchronization. Okay, for the entire grid, for all Feds in the entire grid. Okay, so the rest is the same. Okay, the rest just using the yeah go over all the odd size, and this over all even size. Okay, yeah. So the code is in the version 3. Okay, and I can show you the result. Okay. Yeah. Yeah, I do not run it, but I just show you the result. Okay. So the tail of these two files. Okay. So this is the first one result, and this second one result. Okay. You can see, okay, both are the same. Okay. Yeah. So for the version 2 is I have to separate the even updating or updating to two different kernel. Okay, and this two call this two kernel. Okay, yeah, and then the version 3 is the put both updating even and odd in the same kernel. Okay, but then synchronize is not using the synfet, using this cooperative group. Okay, yeah. So you can see the version 2 is this. Okay, the same. And then version 1 is okay. Yeah. But one thing, as you can see, the difference is this. If you put these two updating in the same kernel, okay, and then this is the version 1, okay, yeah, is the takes this time, okay, yeah, you can see the two is yeah, I think 2 is more time than the 1, right? A little bit more, okay, but it's more or less the same, okay. But if using the version 3, okay, definite more, okay, okay, 2 seconds, okay. So it's takes a little bit more time, okay. And then you can see the gigaflop is a 0.39, right? Then the version 2 is a 0.40, okay, 0.407 or 8. And then version 1, yeah, version 1 is slightly faster, okay. So, but the version 1 is the simulation is not repeatable, okay. You cannot repeat your simulation, okay, with the same initial condition and the same number seed, random numbers generated seed, okay. Okay. So, okay, I think, yeah, there's all 3 different versions of the simulation or using model with GPU and then using the Metropolis algorithm. Okay. Yeah, there's another topic is about the era of the Monte Carlo simulation. Okay, which is yeah, I think I don't have the time today, and yeah, I will cover it next time. yeah, you can look at the slide. Okay. Yeah. Okay. Constant memory. Okay, I already discussed it. So the error estimation, Monte Carlo simulation. Okay. Yeah, because this Metropolis algorithm. Okay. Yeah, this two configuration are actually there's a correlation, not statistically independent. Okay. So the way to estimate the error, okay, using this formula for the completely statistically independent configurations, okay, yeah, is underestimated, okay, yeah. So the variance of the mean is equal to the variance divided by 1/n variance, okay. So, but this only all data have to statistically independent. But the configuration, okay, resulting from the Metropolis algorithm or any Monte Carlo simulation algorithm, they cannot be statistically independent, okay, because they have a correlated, okay, because it was generated according to the algorithm, the Metropolis algorithm, okay, and that algorithm is just every step is a local updating, okay, and this updating depends on the old configuration, okay, old spin, okay, so they could not be statistically independent. Yeah. So you have to add the error due to the correlation, okay, autocorrelation. So add this CM, right? So if they are all statistically independent, then this goes to zero, okay? But since they are not statistically independent, then there's an autocorrelation function, and you have to add this autocorrelation to function. Okay. Yeah. Next time I will discuss this. Okay. Yeah. Today I don't have enough time to cover this. Okay. I think that's all for today. Any questions? Hmm? Yeah. Yeah. It turns out that we don't have too many lectures left until the end of this semester. So yeah, see how far we can go. Okay, yeah, and depends on your your preference. Okay, yeah, yeah, we can still doing the lecture in the final week or skip the lecture in the final week. Okay, so let me know what you think. Okay, but the final homework must be due on June 11th. Okay, since I have to hand in the grade sheet. Okay, yeah, there's a deadline for the grade sheet. Okay, so the deadline for all homework assignments should be due on June 11th. Okay, yeah. Yeah, any questions? Hmm? Okay, if not, let's conclude today's meeting. Okay. Okay.